In this video, I want to look at the definition of a complete ordered field. And what we're going to basically do is we're going to start with this idea. We're going to let F be some set of numbers. We're basically going to be thinking of numbers as something that we can add and subtract. It's okay to be thinking about F as a subset of the real numbers or a subset of the complex numbers, things that you already know how to add and subtract. And what we're going to do is we're going to be thinking about the algebraic structure of F, that set of numbers, complete with its addition and its multiplication. And I want to think in terms of what the phrase complete ordered field means. Now, there are three basic vocabulary words that we have to look at, and they are field, and then ordered, and then complete. And it's important to understand that that's the direction that they have to go. So we've already actually looked at ordered fields, but I want to kind of briefly remind you of what they look like. So if we say that something like F under addition and multiplication is a field, what we mean is that we have a bunch of properties. In particular, we have closure, that if we pick any two things in F and we add or multiply them, we stay inside F. We have commutativity. It doesn't matter which way we add or which way we multiply. In other words, A plus B and B plus A are the same thing. A times B and B times A are the same thing. We have associativity. We can put parentheses wherever we want to in addition. We can put parentheses wherever we want to in multiplication. And again, this is true for all elements inside the field. We also have the distributive law. Multiplication distributes over addition. In other words, A times the sum B plus C is A times B plus A times C. We also have to have identity elements, namely a 0 and a 1. They do need to be separate from each other, and 0 is the additive identity. A plus 0 is equal to A for all elements inside the field. 1 is the multiplicative identity. A times 1 is equal to A for all elements inside the field. We also have to have additive inverses. For every element inside the field, there is a minus A inside the field, such that A plus minus A is equal to the additive identity element, in other words, the 0. And finally, everybody except for 0 has to have a multiplicative inverse. Now, it's important to understand that both the rational numbers under addition and multiplication and the real numbers under addition and multiplication satisfy all of these axioms, so both of these are fields. And that means this is not where the difference between the real numbers and the rational numbers lies. So fields basically mean we have all of the normal properties of arithmetic. An ordered field means that we have all of the ordinary properties of the less than relationship. In other words, we have a field and we have an order relation called less than that satisfies the so-called order axioms. The first order axiom is the transitive law, that if A is less than B and B is less than C, we can conclude that A is less than C. We also have to have the law of trichotomy. If we take any two elements inside the field, they are either equal to each other, or A is less than B, or B is less than A, and you only have one of these three things happening. We can add things to inequalities. If I start with A is less than B, I can add C to both sides and I maintain the inequality. We also know about multiplying inequalities. Multiplying inequalities is just a little bit trickier. We know that if A is less than B and C is bigger than 0, then multiplying the inequality does not change its order. But if I have A is less than B and C is less than 0, and I do a multiply, then I have to swap the inequality sign. AC will now be bigger than BC. And finally, we have the Archimedean principle, that if I take anybody in F, there will be an integer n, such that A is trapped between n and n plus 1, and it might be equal to n. And here again, what I want to notice is that Q under plus and times and R under plus and times satisfy all of these axioms, and so they are both ordered fields. So the order axioms are not where the difference between the rational numbers and the real numbers lie. So the final thing I want to look at is, what does it mean for something to be a complete ordered field? Well, obviously, the first thing that we're going to want is we want F under its addition and multiplication to be an ordered field. And then we also need some kind of a second property. And the second property is going to be this. It's going to say the following thing. If S is a non-empty subset of my field F, and S is bounded above inside my field F, then there's going to have to be an A inside of the field F such that A satisfies the definition of sup of S. In other words, every set S that is non-empty and bounded above inside the field has to have a supremum. It's important to realize that this particular property is usually given the name the completeness axiom. It's also important to understand that S is bounded above in F means there exists a B inside the field F such that B is bigger than or equal to little s for all s's inside the set S. So bounded above means what it always means. And the other thing that's important to understand in the completeness axiom is that the supremum of the set doesn't only have to exist, but it has to be inside the field F. So this is an important note, as is this. The final thing that I want to look at in this particular video is actually I want to ask a couple of questions. So to tie up this video, I'm going to ask the following two questions. Is Q under its addition and multiplication a complete ordered field? And also, is the set of real numbers under its addition and multiplication a complete ordered field? We will explore those two questions in the next video.